Let me begin by saying this. I love the boosted boards. I think they are by far the best and overall greatest electric longboards out there. Their lightweight design, the flexi deck, the great remote and the torquey power is what really makes boosted boards great. I've ridden a few different electric longboards and I would definitely say that boosted board was by far my favorite commercially available board. But I want to use my electric longboard for 15-kilometer long trips that I usually do on the weekends, and I also really like going fast and love riding my e-board with speeds up to 50 kilometers an hour. And boosted board just doesn't have the power and the gearing to go that fast. So as I usually do, I set off to build my own dream board. I want to combine the same flexi deck, the awesome design, the great remote, lightweight but way more torque and way higher top speeds, and of course better brakes and greater range with fast charging were definitely my goal. So here's my journey on how I managed to build my own dream electric skateboard. Almost everything possible is 3D printed on this thing. From the awesome looking battery and vest casing I designed, gears, protectors, and even this insane Firefly e-skate remote. A lot of this stuff is heavily boosted board inspired, as you can already see, because I think they literally produce the best commercially available electric skateboard on the market. But doing a DIY project, you can definitely improve a lot of things and do a lot of stuff better that usually would be way too expensive for mass production. But since I call this thing the boosted board killer, let's compare the specs to each other. Boosted board has a top speed of 35 kilometers an hour. My top speed is 50 kilometers an hour, but you almost never want to go that fast even. The maximum power my board can deliver is 5000 watts. That's 7 horsepower. The constant power is only around 2.5 kilowatts, by the way. Compare the 5000 watts of my thing to the boosted board's 2200 watts. The battery consists of the currently best available high energy density and high power density lithium-ion 18650 cells you can buy. Basically the same type of cells that are used in the old Tesla models. Compare that to the Li-Fi Pro 4 batteries that boosted board uses. They have really high power density but very low energy density. That's the reason why their battery pack is almost the same size as mine, but you have only a third of the range. So what's the range on my board? It's around 35 kilometers, but really depends on your ride style. Of course you can go 50 kilometers an hour, and that just wouldn't be possible on a boosted board. That's why your power consumption can be way higher. But compare that to the 10 kilometer range on a boosted board. And the battery also allows for insane quick charging. So if you're ever in a hurry, you can basically quick charge this thing with up to 30 kilometers of range per hour. Compare that to the 6.5 kilometers an hour of charging rate on the boosted board. And with this awesome remote with its cool features and display, it's by far the most fun electric longboard I've ever ridden and the best thing I could imagine. The battery cases, vest casing and motor guards and everything else was designed by me and will be made openly available for everyone to download. Link will be in the description. So let's go over all the design features I made. Let's start with the push button. This thing directly enables the anti-spark switch. I specifically invented a pre-charging anti-spark circuit for this application. Why you need a anti-sparks and why every single one that you can usually buy online actually breaks all the time, and why you should build my design, I will cover that later. The battery houses 36 cells, which are connected in a 12S 3P configuration, and also a smart BMS with Bluetooth app that I made a video about previously that protects my batteries. On the other side of the switch we have a XT60 connector plug for charging. Now you might be wondering why there are no cables running from the battery to the motor controller. That's because I've hidden them, like on the boosted board, with some very wide cables under the grip tape. Two 4mm bullet connectors will allow a very quick swap for a different battery pack. I'm thinking of adding a LiPo holder or something like that later on. At this point there's no real use for that, but you will notice overall The modular system I went for with the rest of the design too, so everything is easily swappable and can be changed out for anything else at any time. The battery casing is waterproof and every single PCB inside the board is completely coated. It was originally intended that the case fits perfectly on the concave, but sadly plastic stretches and bends a lot when annealing and cooling down. That happened to me in this case, so the print deformed quite a bit. The only solution was to print it again or just design a bigger lid and place some spacers on the sides. Now the design isn't that slick, but it still works. The vest case on the other hand was pretty easy to print. It's very easy to close and pretty watertight if you put some glue around it. But same thing in here. All PCBs are coated, so even when a little bit of water does get in, it can't do any damage to any of the electronics. Everything in there is pretty neatly packed and there is absolutely no space wasted whatsoever. That gives this drivetrain a pretty slim look. The vesks are pressed really hard in there and can't move a single bit. Now here's how I protected the motors. First, of course, I coated the motor hall sensor PCBs, so even when water does get into the motor, it can't do any damage in there. Then I designed this pretty nice cap that goes very tightly around the small gap and protects the motor from like 99% of any dirt and water getting in. Waterproof outrunner motors are pretty difficult to design, but I think I've done my best here, and this thing is pretty damn watertight. To prevent any water from creeping up the cables, I added a heat shrink tube around the cables. Not only does this make them last longer, but a zip tie on top with some instant adhesion glue makes this design incredibly waterproof.
And as you can see here on the logo, it's quite rusty. I've coated absolutely nothing inside. I was absolutely blown away that they look inside absolutely clean. Like, a lot of people always ask me what motors do I use. It says right here, Chalkboard's motor. They're from DIYelectricskateboards.com. And I would actually really like to recommend you guys these because they have great performance, and at 190 kV they are insanely powerful and have some great torque. But if I'm honest, there's one big problem. When I bought these, the magnets were falling out on my one. Like, in the first 200 kilometers I heard like a very, very loud rattling noise coming from my motors. Then I opened them up and saw that all the magnets inside there were completely loose. So now I've basically used some instant adhesion and glued them down. It's just the fact that they used some very cheap glue inside the magnets that basically loosened them up, and they were almost falling out and almost destroying the motor itself. The one main benefit why I would recommend them, because you can fit two of them side by side on the normal 180 millimeters trucks. And that's the reason for me why I need to use them. There are not that many other motors out there that I can use for this specific application.
The specs. Now let's get to the details. I already said that this thing has a 12 in series and 3 in parallel battery with 388 watt hours of capacity. You obviously only want to use like 300 watt hours if you want to get more cycles out of it. The two most important factors for me when choosing the right cell for my application was to find a cell with very high energy density and high power density. For example, cells like the Samsung 25R are great for high power applications because they can put out easily 30 amps, but they don't have the type of energy I want. And the Samsung 35E are the highest capacity 18650s you can currently get, but don't have the power I need. They can only put out like 10 amps. So I needed to find something in the middle, something that has quite high energy density so I can get a long range, but can also put out a lot of amps so I don't lack power. I obviously had to go for 12S. That's the only way to push my motor controllers, the VESC, to its absolute limits. If you go anything lower than 12S on a VESC, you obviously lose a lot of power. I only went for 3 cells in parallel, so I can run every single cell on around 35 amps peak. Now if you look at the datasheet of these cells, they are only rated for around 20 amps, but that's continuous. And I only use my 35 amps per cell for a very short burst. That's only when accelerating, because 5 kilowatts of power will kick your ass and you will fly off your board if you do this for too long. So you can't really withstand the 5 kilowatts of power anyway for a long time. This battery pack gives me a pretty insane power to weight or power to size ratio. Since I only have to go 15 kilometers of range maximum, this pack is more than enough and will even withstand the degradation of time. So even when it only has like 80% of its original capacity, I will still make my 15 kilometer trip. For me, I think this was definitely the right choice. Why I used a smart BMS was pretty obvious if you've watched my previous video about it. Well, if you don't know what a smart BMS is and why you should really use one if you are not using one, you should definitely watch my video about it. The next amazing thing on this vehicle is the pre-charging anti-spark switch. So if you think about an electric vehicle, turning on and off one with a switch obviously doesn't work, since you are drawing a lot of current on the output and would destroy any normal switch out there. So what can be done? You can use a MOSFET, because they have very low resistance and you can push a lot of amps through them. And there are even circuits out there that do exactly that. But there's a very fundamental problem about every single anti-spark circuit I can find out there. They don't work with more than one VESC. They instantly blow up. And in my case, I even added additional capacitors in front of the ESCs, which will even further increase the chance of a anti-spark circuit blowing up. The simple problem is that MOSFETs switch on almost instantly and connect this huge capacity of the ESC directly to your battery, which basically creates a short circuit for a very quick period, and all of a sudden your MOSFET latches up because it just can't handle the 1000 amps or whatever your battery is putting out. I think I will make a separate video about why my anti-spark is so good and why you should build it. But the simple principle behind it is that every time you turn on your vehicle, for a fraction of a second, the capacitors of the EC get in the first step charged. For a very quick period of charging the capacitors, the rest of the system will turn on, which will basically give you the power. You don't even notice it. The only difference you will notice is that your anti-spark circuit won't break anymore. In the battery case, there's only 3 things: the battery, the smart BMS, and the anti-spark switch. On the underside, there are some 4mm bullet connectors that make it extremely easy and fast to remove the battery pack. That will open up new possibilities, maybe for a long range pack or a short range pack, depending on whatever you need. Just unscrew the 6 screws and the pack can be taken off very easily. In the VESC case, there are 2 of the most high power compact motor controllers you can currently get. These are the eSkate ESC 1.2. They are based on the VESC 4.12. They have the latest and greatest hardware and this big alloy heatsink which can allow for up to 90 phase amps, and one of these can do around 3 kilowatts with a 12S battery, and I have 2 of them. And since I don't want to instantly burn down my batteries and my board, I limit them to around 5 kilowatts of peak power. And of course, I mean that's more than double the power of a boosted board. For controlling the VESC, I have also a Arduino Nano connected to a NRF24L01. The Arduino is also hooked up to the VESC and basically sends all the control data to the VESC, but is also reading data from the VESC and sending it to the remote. This remote was not designed by me. It's a community open source project started by Solid Geek. The mechanical side from Solid Geek is absolutely awesome, but the software is quite weird. It was weird, at least, because I rewrote the code. I added a total odometer that counts every single kilometer you will ever ride, and added a bit of information like power, energy used, and many other stuff. Solid Geek used some very weird stuff in his firmware. For example, he used UART to get the data from the VESC, but the PPM signal to control the throttle. That's not quite the smartest move, I think, and very unsafe. I instead used the UART for everything, writing and reading data from and to the VESC. That makes it way simpler to wire up and makes error inputs less likely. Speaking about safety, I added some safety features like a checksum and many other things to protect against wrong inputs. I will provide a link to my code in the description, of course. This remote is absolutely awesome. The screen is always readable even in the brightest sun. The control is insanely smooth and precise and puts the Nintendo Nunchuck I previously used to shame. I've let a lot of people that have never ridden a longboard before ride this thing, and with the Nunchuck they were always easily thrown off the board because you would twitch the controller like a millimeter forwards and this thing would just kick off. But on this remote you can control your board way smoother and way easier. It's a way safer way of riding electric longboards, I think, and hands down the best electric skateboard remote you can get. If you don't have a 3D printer, I think it's a really good option to invest in a ANET A8, which I still think is the best and cheapest printer you can get out there. If you don't want a giant DIY project and build your own 3D printer or whatever, I can also recommend you buy the 3D printed parts online if you want to get this remote yourself. It's the best DIY electric skateboard remote out there, hands down. Reliability. I should maybe address one of the main reasons I built this board. My old board I built last year just wasn't reliable. Water and dust was getting in there very easily and I felt like I needed to fix this problem. Every 100 kilometers with my old board I got problems with the electronics getting dirty or the motors getting destroyed or whatever. And now, because I coated every single circuit board on the inside with silicone and made every box easily sealable with no water or dust having any chance to cause damage. My old motors were also destroyed by some salt water because it was getting onto the Hall effect PCBs of my motors, and also I had a lot of dirt and dust inside my motors, clogging this thing completely up and destroying everything in there. But now with my new design there is absolutely no chance of dirt getting even into the motors in the first place. Old problems with my anti-spark switches failing were also now solved by my new design with my pre-charge anti-spark circuit, as I already explained, but I will do a complete video about this probably. But I still had a problem. Always less than 1000 kilometers or so, any ESC I ever used, any VESC I ever used, somehow the electronics just blew and the VESC was destroyed. And sometimes I was able to repair it and sometimes not. On the new design this problem got better, but still I had to repair one of the eSkate VESC 1.2 because one of the capacitors blew up. And the reason for that is very high voltage spikes. These are more likely to occur on the old VESC designs. And I was running the VESC with around 70 phase amps and 12S. That also increases the chances of a voltage spike occurring. But these giant voltage spikes that destroy your VESC can even happen on less powerful setups, on 10S with 60 amps for example. So is there any way to prevent this from happening? Yes, and it's a very easy fix. See, Benjamin Vetter is a great engineer, his software is awesome, but for some odd reason he forgot to add a TBS diode on the input of the VESC. Weirdly, the engineers over at Inertion added a TBS diode on their FOC box, but in almost every other VESC you can get out there, there is no TBS diode on the input, and they will always break one day or another. So what even is a TBS diode? It's a suppressor diode that conducts electricity above a certain voltage. It's like a switch that turns on as soon as the voltage gets too high and basically eats up any voltage spikes and protects your electronics. The one I chose has a threshold voltage of around 58 volts and starts to get highly conductive at around 62 volts, which is also called the breakdown voltage. And installing this thing is very easy. Simply slap this thing in reverse to the polarity of your input voltage and you are good to go. In my case, the one I will link in the description is even a bipolar one. So theoretically the diode can be mounted either way, it won't even matter. And such an easy fix can make your VESC incredibly more reliable. This VESC doesn't have a TBS diode so far. It's simply going to be pointing from this pin to this pin. You're gonna solder it on there. The other side, this pin is plus and this pin is obviously minus. That's it for the electronics. And your electronics now should never ever again fail. Another problem I fixed was I've always had to replace the bearings many times. But after like 3 or 4 bearing swaps, I found these very cheap 608 2RS bearings online and they work the best. they last way longer than any expensive skateboard bearing I've ever used before. Why? Because they are 2RS. If you want to buy any new bearings, just look for the 2RS. They have a little bit more rolling resistance, but you won't notice that at all on any skateboard. Maybe on a fidget spinner, but otherwise you won't notice it. But are double sealed. They basically have a sealing on the inside and on the outside and are way better protected against dust and rain. Because mine always broke after I rode one time in the rain or so. But these very cheap 40-cent double sealed ones have lasted on my board for more than 1,000 kilometers. And many rides in the rain, and are still good in shape and don't make any rattling noise. Now on my board, of course, there are the typical maintenance things to do. Like I need to check the belt system for dirt or rocks, and every 500 kilometers your belts will rip and you have to replace them. But other than that, you don't have to do any maintenance whatsoever. And even after over 500 kilometers now, my board hasn't broken down a single time. I built this vehicle mainly to learn, and 3D printing almost anything possible was a great learning experience. Printing this huge battery holder, I noticed, for example, the whole thing was warped after annealing it. So I had to redesign the top cover. And while doing that, I thought of new ways I could improve this design if I ever wanted to print something like this again. Now my battery case doesn't sit flush against the concave of the board, but yeah, some things are just not perfect. But in the end, everything just works out, and the board works without any problems. If you want to build this yourself, all the software, all the code I wrote, and the 3D designs will be linked in the description. I will make a video explaining a few things more up close in the future, for example my anti-spark circuit, as I already said. So if you enjoy this type of content, if you want to see more insane electric vehicles and anything like that, please subscribe to my channel and also hit the notification bell if you don't want to miss any future projects. Thank you guys so much for watching. See you soon. Ciao.